All right, we're going to continue our topic of exponential functions. Now we're going to talk about the natural exponential function. The natural exponential function is an exponential function whose base, a, so remember our base, a, is some number greater than 0, not equal to 1. Our base is going to be what we call the number e. All right, and number e in math can be proven using limits. As you can see down here, e is defined as the limit as x approaches infinity of 1 plus 1 over x raised to the x power. Right, so as we were to graph this exponential model, right, and look at its limit, as this, again, graph goes to infinity, you'll see x converge in. Again, as we go to infinity, we'll see the output converge in on what we call the number e in math. We get closer and closer to 2.71828. And this is an irrational number. This decimal goes on forever. But again, it's a rounded number here of 2.718. It's usually what we think of as we think of the number e in math. And e is used in a lot of applications. We'll use it in exponential growth and decay. We use it in business when we talk about compounding interest continuously. So it's used to model a lot of different everyday applications that we look at. With that said, we talk about different numbers in math, right, using these different names. We know in circles, when we talked about area and circumference, we introduced the number pi, right? We think of pi as 3.14, but it's an irrational number, a non-ending decimal. Pi, again, remember, is proven by looking at the ratio of circumference to diameter with a circle, and that proves our number pi, right? Now, as we look at the graph of an exponential model, base e, right, it falls under our characteristics of the graph of a to the x, right, where our base a is some number greater than 1. So we know, again, it's an increasing function for all x, since that number is greater than 1. Had it been less than 1, right, had it been number greater than 0 and less than 1, it'd be decreasing exponentially as we, again, approach infinity with x. With that said, of course, our y-intercept point, we know is 0, 1. Of course, the y-intercept of any exponential model, a to the x power, right? We know we have a y-intercept at 0, 1 because anything raised to a power of 0 or some number greater than 0, not equal 1, right? If we raise that to power 0, it's going to equal 1. So you can see our y-intercept of 0, 1, that characteristic. And then it has a horizontal asymptote right here at the x-axis, the right line, y equals 0 is where our exponential model converges on as we go to negative infinity on the x-axis. It gets closer and closer and closer to this line y equals 0. Now we'll never get there. As you remember, the range of exponential models, a to the x, is all values greater than 0, right? It takes place on the positive side of the y-axis. Again, a couple other points I've listed here. We know if we let x be 1, we know e to the 1 power would be e. So it passed through the point 1e, of course, e being around 2.718. Again, if we let x be negative 1, we'll look at a negative value. We know e to the negative 1 power is 1 over e, right? 1 over 2.718, which again is right here on this graph. But you can see a graph of your exponential model and those characteristics. It says here to graph the following exponential functions using your transformations. Make sure you state your asymptote, our horizontal asymptote with exponential models, and tell me domain and range like we did in our previous example. Let's take a look at this first example. So here we got a base e exponential. So before we begin graphing this function, let's go ahead and build in the graph of the parent model, right? The graph of e to the x power. So again, as we graph in the parent model, we know the y-intercept point will be here at 0, 1. We know we're going to flatten out as we approach the line y equal to 0 will be our horizontal asymptote if we graph in e dx, and it'll again be increasing for all x values. As x gets larger, y gets larger. Right, it's an increasing for all x, being this is a graph of form a to the x ray greater than 1. So here's a quick sketch of the graph of e to the x power, which is the parent, right? That's the parent model of this graph here in example A that we're trying to get. So let's use that graph and some basic transformation characteristics to graph in the function that we're looking for. And let's do it in a different color. Let's put it in a color here. We'll do green here. All right, with that said, let's go ahead and take care of this first change. One difference that I noticed from e to the x is we're subtracting a 3 from x. And we know from subtracting a 3, right, from x, that causes a horizontal shift of our graph of e to the x. So we need to shift to the right 3 units, right? When we subtract a positive 3 from x, right, we're going to be adding 3 to every x coordinate on the graph of e to the x. Right? If we added 3 to x, that'd be a minus negative 3. We would shift it left 3 units. Right? If it had been x plus 3, that's x minus negative 3. But with that said, so as we graph it over here, so 0, 1, let's go ahead and move right 3 units. We know, again, that would move over here to the point 3, 1. Now, our horizontal asymptote would still be at y equals 0, right? Only thing we've done is pushed our graph to the right 3 units. So again, we can dash in this graph right now, but here's the graph of e to the x power with a minus 3 on the x term. So f of x equal to e to the x minus 3, right? We've got a sketch of it right now in front of us. Now, of course, we got another change, right? We got a plus 2 in here. So we've shifted right 3 units. Well, we know this plus 2. We know anytime we add or subtract a constant to any function, moves that parent graph up or down, right, vertically on the y-axis. So plus 2 units, right, would be a shift up 2 units. We would add 2 to each y-coordinate. Now remember, in a vertical shift, as we go up 2 units, right, so we go up 2 units on the y-axis, will be at 3. So right here is up 2. I'm going to go ahead and plot in this point. So as we plot in this point, now let's go ahead and erase this last graph. But 3, 1, right? We know the point 3, 1 is going to move up here to 3, 3. We're going to add 2 to every y-coordinate. Now with that said, again, we've gone right 3 units, again, and up 2. So we'll make a little note. Again, right 3, up 2. So 0, 1 and up 3, 3. Now one key change is our horizontal asymptote. It moves up 2 units. We got a vertical shift up 2. So let's go ahead and draw in this new horizontal asymptote, which we're going to need, right, to get an accurate graph. So y equal 2, right, our horizontal asymptote for our new function. So now I can clearly graph in what this graph of this model would look like. So you can see it here in green. Right, here's the graph of e to the x minus 3 power plus 2. So with that said, our horizontal asymptote, which they've asked us to state, is at y equal 2. That leads us to the range, and we'll go ahead and write the range down here, which is asked us to define. Where does this graph take place on the y-axis? All y values greater than 2, right? 2 to infinity would be our range in interval notation. Of course, our domain, as always, the x values, the inputs, we can plug anything we want in and get an output. There are no undefined values, continuous function from throughout the domain negative infinity to infinity. So with that said, domain is all real numbers x. So again, that's a natural exponential model. All right, well, let's take a look at the second example. Let's do one more. Example B. Let's go through its characteristics. Now with that said, let's go ahead and look at the parent model. So as we graph in e to the x, again, it's another base e exponential. E to the x, y equals 0, the horizontal asymptote there at the x-axis. Let's go ahead and label that. Increasing for all x, continuous, 1 to 1. Here's our sketch, right, of the graph of e to the x power, which again is our parent. For this function here, we're trying to graph an example B. Continuous, 1 to 1, all the characteristics, graph a to the x, a, b, and greater than 1. E, again, is that number 2.718, a natural number, natural exponential function. With that said, let's go graph our new one. And again, we can put it in a different color. We can use green again if we like. We got a few changes. Let's go ahead and take care of this change out here in front. We've got a negative. Now we know a negative, if you remember back to transformations, causes reflections. So we're going to reflect our graph. Now what we reflect about depends on where your negative is. If we multiply our function by a negative, like we've done here, we're going to reflect our graph across the x-axis. We're going to turn it upside down. So with that said, let's go ahead and do that. So every y-coordinate, we're going to multiply by -1. We're going to reflect the x-axis, right? We know that xy would become x negative y, right? As we multiply by a negative. So 0, 1, for example, would move down here to 0, -1. And let's go ahead and sketch in. I'll dash it in, right? It's mirror image right across the x. So there's a graph right now of f of x equal to negative e to the x. So that takes care of the negative. Now we have a couple other changes. We got a +4. So again, this is the same thing as saying x minus -4. So that means we've got a horizontal shift, right, to the left 4 units. We're going to subtract a 4 from every x-coordinate. So 0, -1, let's go ahead and track that. So if we go left 4 units, we're going to be over here at the ordered pair of -4, -1. So we can go ahead and plot that point. Again, I'm going left 4 units. All right, still at y equals 0 is my horizontal asymptote, right? Still decreasing here for all x now as we flipped across the x-axis. But that shifts it to the left 4 units, right? We're going left 4. So -4, -1. And then our last change, right, we got a 1, and it's a +1. So we're going to move it up 1 unit, right? We go up with plus, we go down with minus. So a vertical shift. So we look back at our graph. Right now we're at -4, -1. Well, as we go to our final place, as we look at our x-intercept point now, -4 is 0. Now this also affects the asymptote. We did have a horizontal asymptote at y equals 0. Well, we're now going to have a horizontal asymptote at y equal to 1. Right? Y equal 1 is our new horizontal asymptote. We've had a vertical shift up 1 unit. So as we're coming from -infinity, it's going to come from 1 on the y-axis. And again, as we go through and sketch in this graph, right, here's the graph of our function there in green. And we could erase everything else, right, that we have there. And again, as our references. Now, with that said, it says state the asymptote, which we've done, y equal 1. Stating the domain and the range. We know, of course, the domain is all real numbers. That doesn't change. It's always true with exponential models. E to the x, a to the x, right? A being some number greater than 0, not equal to 1. Now our range is dependent on, again, range lists the y values, is dependent on that horizontal asymptote that we have. So at y equal 1, that's what we converge on. We get closer and closer to it. So our range is from -infinity, let's shade it in together here on a y-axis, all the way up to 1. So all y values less than 1. So parentheses on 1 would be our range. So again, just using basic transformations and using our knowledge of what exponential models look like, right, we can easily sketch the graph of exponentials.